this video, we'll understand the interpretation of various aspects of multiple linear regression algorithm. Similar to our understanding of two variable or bivariate regression model, this expression here represents the conditional mean or expected value of y given the values of x1, x2 and xn and so on. So this is very similar to the expression that we saw earlier, expected value of y given x. Here, instead of single independent variable, we are considering all the independent variables from x1 to x1, and therefore this represents the expected value of yi given all the xi's. This is called the conditional mean or expected value of y given the fixed values of xi's or conditioned upon the fixed values of xi. Notice the coefficients beta 1, beta 2 and so on up till beta n here. These are called partial coefficients. For example, this beta 1 is the partial coefficient and it measures the effect of x1 on this variable y net of any effect from any other explanatory variables, that is xi, or in other words, keeping all the other xi's constant. If all the xi's are held constant except x1, then beta 1 will represent the impact of x1 on y. Let us introduce a very important parameter, which is r square. This r square represents the part of variation of variable y which is explained by this model. I repeat, this r square represents the variation or variance in the variable y, which is the dependent variable, which can be explained by the model, this all the xi's and coefficients to put together. The computation is very simple. Basically, this is explained sum of squares divided by total sum of square, which is equal to 1 minus residual sum of squares upon total sum of squares. Let me give you a little bit background on this. Recall that the values of y on xy axis are provided like this, and this is your fitted line. So this is the total, let's say this is yi, then this is the total gap. Sum of squares of these total yi's will be total sum of squares. However, this much part is explained. This much part is explained part. So this squares of these distances would be explained sum of squares, and this is unexplained part. These are the error terms. So this is unexplained or residual sum of squares. So here explained sum of square, that means these sum of squares divided by total sum of squares, which are these total terms. Total sum of squares is the explained part, ratio of explained part. This can also be computed as 1 minus residual sum of squares upon total sum of squares, where the sum of squares of these distances is called residuals. This remains same whether we are talking about bivariate regression or multivariate regression, as we are seeing here. A more improved version is also computed in the form of adjusted R square, where a small adjustment is made. Here, instead of using RSS and TSS, we divide these residual sum of squares and total sum squares by their respective degrees of freedom. For RSS, the degrees of freedom are n minus k. Here, n is the total number of variables. Here, n is the total number of observations in the sample. K is the number of coefficients excluding beta naught. So all the beta 1 to beta n, all the coefficients excluding beta naught, divided by n minus 1. N minus 1 is the degrees of freedom for TSS. So I repeat, RSS upon n minus k, where residual sum of squares has n minus k degrees of freedom, where n is the total number of observations in the sample and k is the coefficients from beta 1 to beta n, and TSS divided by n minus 1 degrees of freedom, where n is the total observations. This is often referred to as mean sum of squares of RSS, mean sum of squares of RSS, that is residual sum of squares, and mean sum of square of TSS, that is total sum of squares. Now, these n minus k and n minus 1 are called degrees of freedom. Please notice this adjusted R square is very interesting entity here. If we rearrange the expression for R square and adjusted R square, we get something like this. Please notice, in R square, in this expression, we are putting a certain additional penalty in the form of these n minus 1 upon n minus k. That means the more the number of variables, the more the number of these k's or variables in the model, this R square is penalized in the computation of adjusted R square. That means the more the number of k's, the lower the value of adjusted R square. So there's certain penalty that this expression puts on R square, and therefore this adjusted R square, which is after adjusting for these degrees of freedom, it puts a certain penalty for addition of variables. The reason being, the normal R square can be easily inflated just by adding the number of variables, small variables where the contribution to the explanatory power is so low that they are not very important, but still if their numbers are too large, the R square value is inflated. So this penal term, this penalty is inflicted on this computation, so that there's a trade-off for adding more variables, which in the form of explanatory power to the model as well as this penalty, and therefore the resulting expression adjusted R square would identify whether the addition of variable is important or not. Lastly, another very important aspect of this model is the coefficients or estimates of the coefficients. Beta naught hat and beta 1 hat, these are simply the estimates of the coefficients using OLS estimators. Based on OLS estimators, these estimates are made. These estimates have some variance. So in repeated samples, these estimates have variances, and the square root of the variance of these estimated parameters indicates the error in estimation or standard error of the estimate. So if you have repeated samples, these beta naughts will have a distribution. Estimates of beta naught will have a distribution, and higher the standard error of this estimate or the variance of this estimate, poor the estimator. Remember, we said that T statistic, which was very important, is coefficient upon standard error of estimate. The higher the standard error of estimate, the lower its T value and lower its significance in the regression model. So for us, the better model or better estimator where SE is lowest, standard error is lowest, given certain assumptions that we made earlier about heteroscedasticity, autocorrelation, multicollinearity, and so on, OLS estimators are supposedly the best in class estimators available with us. And that is why we discussed OLS estimators in great detail. To summarize, in this video, we discussed the interpretation of multiple linear regression. We noted that the expressions such as conditional expectation of the dependent variable remains similar as bivariate regression model. The interpretation of coefficient is also very simple. These are simply partial coefficients which reflect the impact of a corresponding variable on the dependent variable, keeping all the variables or all the variables constant. We also discussed the computation of R square measure and adjusted R square measure. We noted that adjusted R square measure provides slightly improved version of R square where we adjust for addition of more variables, and therefore it recognizes the fact that addition of more variables simply just to increase the explanatory power is not desirable, and therefore it puts a penalty or a penalizing term, penalizing adjustment to reflect that variables should contribute significantly and not just in small explanatory power. We also noted that it is desirable that the estimators of the coefficient like beta naught hat and beta 1 hat, these estimators should have lower variance. That means their standard error of the estimate should be lower, which increases the power of the estimate or power of the regression, so that the t values and therefore the ability to reject the null and bring out its impact on the model more efficiently. So for that, we need estimators with lower standard errors. In this backdrop, OLS estimators are considered to be the best estimators as they offer the lowest variance in the entire class of linear estimators. In this video, we'll briefly review the key assumptions behind the CLRM, that is classical linear regression model. The Gaussian standard or classical linear regression model as it is called makes 10 very important assumptions. The first assumption is that the linear regression model is linear in the sense it is linear in parameters. For example, let us look at these three diagrams. This one, y equal to beta 1 plus beta 2x plus beta 3x square, is linear in parameters but non-linear in variables, which is x square term. However, it can be estimated with the CLRM because it is linear in parameters. On the contrary, this one, y equal to e to the power beta 1 plus beta 2x, is non-linear in parameters. Although there are transformations, as we'll see, that can make this expression linear, but as of now it is non-linear in parameters. Look at this expression. Earlier we had a quadratic expression where x square term was there. Here we have x cube term, but still it is linear in parameters and therefore directly estimated. It can be directly estimated through classical linear regression model. Second assumption here is that the values of x in repeated samples are fixed. That means they are not stochastic. and they do not have any random component. So they are fixed in nature. Unlike y or error term, they are not stochastic. They don't have any probabilistic distribution. They are fixed and estimated with certainty. There is no stochastic aspects of x. Next, and a very important assumption is that zero conditional mean of the disturbance term mu I, or the expected value of disturbance term mu I or error term is zero conditioned upon each xi. For example, let's say we have x1 variable corresponding to which there are number of y's, and for all these y's, error terms mu1 i's would be estimated. Mu1, all these mu i's, if we take the mean of these mu i's, since it is for only x1, then mu I x1 equal to 0. Similarly, for x2, all the mu i's, mu1 I, mu1 2, mu2 2, and so on, all these mu i's will be 0. So conditional mean of all these error terms for given xi should be equal to 0. The next assumption, assumption number 4, is of homoscedasticity or equal variance of these error terms. So like we said earlier, for a given value of x, the variance of mu I is same for all the xi's. That is, conditional variances of mu I are identical. That is, expected value of mu I minus expected value of mu I xi raised to the power 2 is constant and equal to sigma square. If they are not constant, that means they are varying with xi's. For each xi the variance is sigma square, then this is called heteroscedastic variance, and it creates problems. That means the solution that we obtain for beta naught hat, the closed form solution that we obtain for beta naught hat and beta 1 hat in, and so on and so forth for other coefficients will not remain valid. Look at this diagram here. Here, with the assumption of homoscedasticity, the variance of error term for each x are same. Notice, for each xi, the variance of error terms is same. However, here the variances are different for different xi's, and therefore it has heteroscedastic variance of error term. In this particular case, the solution, the closed form solution for coefficients beta I hat that we obtained earlier, we saw earlier for the simple linear regression, will not remain valid. Another very important assumption, assumption number 5, is the no autocorrelation between the disturbances or error terms. So for any two values of xi and xj where I equal to not j, the correlation between mu i's which are corresponding to xi and mu j's which are corresponding to xj should be 0. In symbolic terms, mu I and mu j, the covariance between mu I and mu j, given xi xj, which is also equal to expectations of this expression into this expression whole square, or expectation of mu I given xi into mu j given xj, because this expectation is anyway 0, expectation of mu I 0 and mu j is also 0, so this simplifies to mu I given xi and mu j given xj, and this is equal to 0, which is also a way of saying that correlation between mu I mu j given xi xj is 0. So this can also be said, because correlation is nothing but normalized or standardized form of covariance. So we can say that covariance between mu I mu j is 0 given xi xj, or correlation between mu I mu j is 0 given xi xj. If there is some correlation, then that can also be examined visually before going to the mathematics of it. For example, if there is no autocorrelation, then the error terms will be plotted randomly without any pattern. If there is positive autocorrelation, then error terms will plot like this with each other. It indicates positive correlation. And if it is plotted like this, then it indicates a negative correlation between error terms, that is mu I and mu j's. Assumption number 6, another very important assumption, is that mu I, the error terms, and xi are not correlated. This is very intuitive assumption, because we said xi is fixed, it is not stochastic, it is taken from outside and is not getting affected by the process. So mu I, which if the model is correctly specified, all the relevant influences are taken with xi's, mu I should not be correlated with xi, which is to suggest that covariance between mu I and xi, which is represented as this term, expected value of mu I into expected mu I, and xi minus expected value of xi, this should be equal to 0. Notice here, we already know that the expected value of mu I, this is 0 already. So this expression simply becomes covariance of mu I xi simply becomes expectations of mu xi, which is this term, which is 0, which in simple terms says that correlation between mu I and xi is 0, because like we said earlier, correlation is nothing but standardized form of covariance. So mu I and xi are not correlated, which is our assumption 6. Then the remaining assumptions are quite intuitive as well. These remaining 4 assumptions are assumptions 7, 8, 9, 10. The 7th being the number of observations must be greater than the number of parameters to be estimated. In fact, for a better estimation, the number of observations should be much larger than the parameters to be estimated. A good thumb rule should be that number of observations should be at least 5 times the number of parameters. The x values, the independent variable must have some finite variance. For example, if the variance is very low or if all the x values are almost same, then the model cannot be estimated, or even if estimated, the estimates are very poor. The regression model is correctly specified, which means all the relevant influences, that is the x size, are taken in the model, and those that are left or not considered should be very small, that even if they are mixed with the error term, because we are not accounting for them specifically in the model, they should not create any trouble in estimation. Lastly, there is no perfect multicollinearity. That means there should be no perfect relationship between the independent variables of this form. So if it is of this form, this indicates that one of the independent variables can be perfectly explained by the remaining variable, and in this case the model will be indeterminable. It cannot be determined. To summarize, in this video, we reviewed and examined all the key 10 very important assumptions of classical linear regression model. In this video, we'll introduce blue properties of OLS estimators. OLS estimators are often considered to be as best linear, unbiased, and efficient estimators. These are called blue properties. We already know that OLS estimators are linear in parameters. In addition, there are two very important properties, that is unbiased and efficient. Let us start with the unbiased estimators. Any estimator that has its expected value same as the true population parameter. For example, if we are trying to estimate beta 1 using some estimator beta 1 hat like OLS estimator, and if the expected value of this beta 1 hat in large repeated samples, if in repeated samples the expected value of beta 1 hat is same as the true population, then it is called unbiased estimator. However, if the expected value is different, for example this curve, notice this, if the beta distribution, the distribution of the coefficient here and expected value is somewhere here which is different from the true beta, then this is unbiased estimator. In contrast, the blue one, this one, is called unbiased because its expected value is somewhere around true beta, and such estimators are often called unbiased estimators. It is considered that if certain assumptions that we discussed regarding multicollinearity, autocorrelation, heteroscedasticity, the 10 classical assumptions, if they are held, then OLS estimators are considered as unbiased estimators. Next, we have efficient versus inefficient estimators. Estimators with very low variance or standard error. Standard is nothing but the variance of estimator. So if the variance of estimator is low, it is called relatively efficient. In this figure, this estimator has a lower variance, lower standard error as compared to the dotted one. The solid blue line has lower variance as compared to dotted one, and therefore it would be considered as more efficient as compared to this. Across different classes of estimators, OLS estimators are said to be best in terms of their efficiency. That means they have the lowest standard error of the estimate. If these two properties of unbiased and efficiency are combined, it is said that for OLS estimators in large samples, they are more, their expected value converges closer and closer to the true beta, and they become more and more efficient. That means their variance becomes lower and lower, and therefore the combined property of efficiency and unbiasedness is often referred to as consistency. What is consistency here? Consistency is that in large samples, the expected value and the expected value and variance converge to true beta. That means the estimate converges to true beta. Its expected value becomes closer to true beta and its variance comes lower and lower. So essentially it converges to true beta in large samples, which is called the consistency. Combining these properties, OLS estimators are best in class, and therefore they are often referred to as best linear, unbiased and efficient estimates. To summarize, in this video, we discussed the blue property of OLS estimators. We noted that across all the samples, across all the estimators, OLS estimators are best linear unbiased estimators, and combining the property of unbiasedness and efficiency, they are consistent estimators as well. That is, in large samples, the sample estimates converge to population parameters. Classical linear regression model, CNLRM, and hypothesis testing part 1. In this video, we'll introduce the normal distribution and its application in classical linear regression model for hypothesis testing and estimating the significance of coefficients or parameter estimates. Recall the discussion on normal distribution. A simple normal distribution on returns have daily price changes or returns on the x-axis here, on the horizontal x-axis, and on y-axis we may have frequency of days or percentage of days. A fitted normal distribution would look something like this green bell-shaped curve. While the bars are actual returns, the continuous shaped normal distribution can be superimposed on this. The important aspect of normal distribution is that it can be simply defined by two parameters. One is the mean, which is mu, and its variance, sigma square, where sigma is the standard deviation. Using just these two parameters, we can define a normal distribution, and as we will see in this video, the application of normal distribution considerably improves the quality of analysis or regression analysis with hypothesis testing and estimation of significance of parameter estimates. A version of normal distribution which is most often employed is called standard normal distribution. Most of the properties of normal distribution, in fact all the properties, remain similar, except that on x-axis, instead of the actual values, say returns, we use the scaled or normalized or standardized return, that is x, which is the value of return, minus mean upon standard deviation. So it is normalized so that its mean is 0, mean of 0, this distribution will have a mean of 0, and standard deviation of 1 because of this transformation. On the y-axis, instead of frequency or percentage frequency, we use something called probabilities, or rather probability densities. So for example, each point will represent a particular standardized return in Z form, and on y-axis we'll have the corresponding probability, which is essentially a probability density, the probability corresponding to this point, which is essentially nothing but probability density. So it would make more sense to have a segment of strip on the x-axis. So the area will represent the probability of observing return in this window, which is represented by a z interval from x1 to x2, where x1 and x2 can be mapped to certain return. For example, from z or -1 to +1, that is in terms of standard deviation, this essentially represents the standard deviation form of returns. So -1 to +1 standard deviation, we have 68.26% of return, ±2 standard deviation area, that is 95.44% of the probability will lie within ±2 standard deviation, and within ±3 standard deviation we have 99.74%, and this is irrespective of different returns because this is now in standardized form. So we can simply say that within if it follows normal distribution, then as per standard normal distribution, irrespective of mean, the mean and standard deviation can be anything. If it follows normal distribution, then for standard normal distribution, these properties will be held no matter what are the mean and standard deviation. That means within ±3 standard deviation you have 99.74% of the probability, within ±2% you have 95.44% probability, and within ±1% there's 60.26% probability that observations will lie within this. Now with this introduction of normal distribution, we can apply the hypothesis testing concept on our parameter estimates beta naught hat and beta 1 hat, because hypothesis testing and inferential statistics are required for sample parameters. we need to draw inferences about population parameters using these sample estimates of beta naught hat and beta 1 hat. And more clearly, to be more precise, we would like the estimated parameters, these beta naught hat and beta 1 hat, to be as close as possible to the population parameters, that is beta 1 and beta naught. Now, please remember why these beta naught hat and beta 1 hat are different from beta naught beta 1, because in repeated samples, these beta naught hat and beta 1 hat will be different because there is certain randomness introduced because this error term. So this error term introduces randomness in the model, and because of that the estimates are not same as population parameters. Every time you change the sample, you will obtain certain different beta naught hat and beta 1 hat and other population parameters. Please note, because this randomness is introduced by this error term, the sample coefficient estimates, that is beta naught hat and beta 1 hat, will also have a probability distribution, and this probability distribution will be similar to the error term because this randomness is introduced by this error term itself. And therefore every time you change the sample, you will obtain different estimates of beta naught hat and beta 1 hat. And therefore if you want to make any inference about beta naught hat and beta 1 hat, you need to know their distribution, which is essentially the distribution of the error term itself, because this is the one causing randomness in beta naught hat and beta 1. So we make the following assumption about the error term in the model. Remember the simple model y equal to beta, this model which we extended to multiple linear regression where this mu was the error term. So the following assumptions are made about this error term. First, the expectations of this error term or the mean of this error term is 0 first. Second, we assume that the variance, that is expected value of mu I minus expected mu I square, or this, because this is 0, is same as sigma square. So this is homoscedasticity. The variance of error term is constant. Second, the covariance or correlation between mu I and mu j, because this is 0, it converges to this expression, is also 0. That means mu I and mu j across observations I and j are not correlated. Combined, the assumption can be written as in this form, that is mu I is distributed normally with a mean of 0 and variance of sigma square with the 0 autocorrelation. Please note that normal distributions, like we said, are very easily defined just by two parameters. One is the mean mu and variance sigma square. Now, as we have made the normality assumption and previous other classical linear regression model assumptions that we discussed, 10 assumptions plus normality, OLS estimates are blue estimates, that is they are best linear, unbiased, efficient and consistent estimates, as we discussed in the previous video. And these, therefore, since they are consistent, these estimates converge to their true population values as sample size increases. The model, as we have already seen, yi equal to beta naught hat plus beta 1 hat xi plus mu I hat. Here the predicted values of yi are written as yi hat, which is beta naught hat plus beta 1 hat into xi. Now please note, the mean of, it is assumed that the mean of beta 1 hat or expected value of beta 1 hat is same as the population parameter, because if these assumptions are held, then the expected value of beta 1 hat is same as beta 1 and variance of beta 1 is sigma beta 1 square. And to summarize these two definitions, we have beta 1 hat distributed normally. So this represents that beta 1 hat is distributed normally and its mean is beta 1 and its variance is sigma square beta 1 hat. So this is the combined expression for these assumptions. Now we can also translate these assumptions that we discussed in the previous slide in the standard normal distribution format. Recall that this z, or the standard normal version, is the value itself beta 1 hat minus its mean, which is the estimate of population. This is expected to be same as population parameter. So beta 1 hat minus its mean divided by standard deviation of beta 1 is the standardized version, which is z. And like we said, this z is distributed normally with a 0 mean or expected value and a variance which is 1, because it is the standardized version. So it is normally distributed with a mean of 0 and standard deviation of 1, and it helps us in doing any kind of hypothesis testing and inferential statistics. To summarize, in this video we introduced the normality assumption with error term. Since the error terms are the ones introducing randomness in the population parameter estimates or sample estimates, therefore the sample estimate itself is normally distributed, the beta 1 hat, beta naught hats sample estimates, Normal distribution, because normal distributions are very easily defined with just two parameters, that is mean and variance. And if these assumptions are held, then the expected value of beta 1 hat is same as beta 1, which is the population parameter. So the sample estimate converges to population parameter estimate if the assumptions are held, as we discussed. The classical normal linear regression model assumptions are held. Its variance is variance of beta 1 hat, which we called as sigma square beta 1 hat, and which is this sigma square beta 1 hat, and therefore we said that beta 1 hat is normally distributed with the mean of beta 1 and variance of sigma square beta 1 hat. We also saw that in standardized form, this is represented by the statistic Tz, which is, since it is standardized with this formula, it has a mean of 0 and a variance of 1 and distributed normally. In the next video, we'll see the application of this normal distribution and conclude its role in hypothesis testing and making inferences about the coefficient. In this video, we'll conclude our discussion on hypothesis testing with classical normal linear regression model. Please remember, in repeated sampling, the point estimate, that is beta 1 hat, converges to population parameter, which is beta 1. This is to suggest that if you have number of samples, the mean of beta 1 hat will converge to two population parameter beta 1. However, we do not have the luxury of working with many samples, and often we are left with one sample. Even that is a very small sample as compared to the overall population. And therefore, the accuracy of this point estimate of this beta 1 hat is important. How reliable is this estimate? Because this single estimate definitely differs from the true population parameter. And therefore, the reliability of this estimate is measured by standard error. Please recall that in OLS estimation of regression model, each parameter estimate, that is, for example, beta 0 hat or beta 1 hat, is estimated with some error. The square root of the variance of this estimated parameter indicates that error in estimation, or essentially the precision of that estimate. So the variance of this parameter estimate, we take the square root of that, which becomes the standard error of this estimate. Let us examine how this standard error plays a very important role in hypothesis testing and confidence interval estimation around this coefficient. In the hypothesis testing procedure, you set up a confidence interval. For example, let's say you want to be 95% confident in your estimate of that coefficient or parameter estimate. Then there is a 5% possibility or 5% chance you are willing to take where you may be wrong. And therefore, if you have taken this 95% region of confidence you are considering, then the remaining 5%, which is distributed in two half regions, 5% divided by 2 and 5% divided by 2, which is 2.5%, is called critical region or region of significance where you may be mistaken. So this is the region which you are willing to take a chance where you may be mistaken. 2.5% on the right and 2.5% on the left, which is overall 5%, because you have taken you are willing to take a 95% confidence. Let's see how this works in the case of regression. Let us say you hypothesize the population parameter as beta 1, which means if it is a simple linear regression model, you are estimating a regression like this: beta 0 plus beta 1 into x, and you estimate a coefficient of beta 1. Now, the way the convention suggests you consider this beta 1 or hypothesize it to be 0, which has a practical implication that if beta 1 is 0, x, our variable of interest, has no impact on y. This is how the convention works. So you assume that you start with the hypothesis that beta 1 is the 0, or your true population parameter is 0, which means x does not affect y. Now you want to set up a 95% confidence interval. And therefore, if you want to set up a 95% confidence interval, which is 1 minus alpha, your alpha or significance level is 5%. So you set up a 95% confidence interval around your population estimate beta 1, which is 0. You set up this confidence interval and you are willing to take a 5% chance, 2.5% on the left and 2.5% on the right, that you may be wrong as well. Practically, you are assuming that beta 1 is 0, that means x does not affect y. So this is your essentially your null hypothesis. And if this null is rejected, you consider a null that beta 1 is 0, and if your estimate falls in this region, you tend to not reject your null. However, if your estimate falls in this region, which is the significance region or critical region, then you reject the null and say that beta 1 is not 0, it is significant, and the implication is that x indeed affects y. So there is a relationship between x and y if you are able to reject the null. Now, in practice, along with 95%, we also check the significance with 90% and 99%. That means this value, in case of 90%, this value is 5% on the left and 5% on the right. In case of 99%, it is 0.5% on the left and 0.5% on the right. That means 1% significance. Now that we have seen standard normal distribution, we also know that if this is a normal distribution, then for each value of probability, whether it is 5%, 2.5%, we have a z value. So depending upon the area in this region, we can find a relevant z value corresponding to each point that we have already seen. In practice, we have small samples, and often population variances are not known. So instead of using z parameter, we make use of student's t distribution, which is very similar to standard normal distribution. Only minor difference is that student's t distribution has relatively fatter tails. It has fat tails, which means for any hypothesis testing, rejection of null requires more evidence. So it needs more evidence to reject the null, and therefore because we work with small samples and we do not want to make any major mistakes, we tend to work with student's t distribution. However, the procedure remains exactly similar. Whether you use standard normal distribution or student's t distribution, the procedure is exactly similar. However, in practice, we tend to do hypothesis testing with regression coefficients using student's t distribution, as we'll see in our practice example, because it requires more evidence to reject the null, and therefore if we are rejecting the null, we are more confident. So we try to find the corresponding t value corresponding to this alpha value. We try to find this t value, which is on this side. Left side it is minus t alpha by t by 2 or plus t alpha by 2. Alpha by 2 indicates that this t value is corresponding to alpha by 2. So in the t table, t statistic table, we take the values which are corresponding to plus alpha by 2 and minus alpha by 2. They are same because of symmetry in the distribution, they are same. Now the way it is done, you compute the relevant t values. You compute the relevant t values or critical t values corresponding to these alpha by 2. For example, if alpha is 5, then you compute the t value corresponding to 2.5% level on the left side and 97.5% on the positive side, right side. So you compute t values corresponding t values. These are called critical t values, which is plus minus t alpha by 2. One for 2.5% on this side, critical value, and one for 97.5. This is in the case of 95% confidence interval. You can find the relevant values similarly for the 90% or 99% level of confidence. Once you compute these critical or significant t values, you compare them with the t value that is obtained in the sample. So you compute a sample t value which is there for your sample, and you compute if this t values is larger than this plus minus t alpha by 2, that means it falls on the right side, either on the right side in the critical region or on the left side of the critical region, then you reject the null. That means you say that beta estimate of beta 1 hat or beta 2 hat or whatever is estimate is under consideration, it is significantly different from 0. It is not equal to 0. If it is on this side, that means it is negative, and if it is on this side, right side, it is positive, but it is significantly different from 0. That means it is not 0. And therefore we are rejecting our null and saying with that level, let's say in this case 95% confidence or 5% significance, that beta 1 is significant and x, the variable of interest, indeed affects the dependent variable y. So just to summarize the discussion, you assume a null hypothesis which is called H0 that the true population parameter beta 1, which is assumed to be 0 in most of the cases, and therefore your alternate hypothesis H1 is that true population parameter beta 1 is not equal to 0, or the variable of interest, which is xi, affects the variable y. The decision rule here goes like this. You construct a confidence level of 1 minus alpha, where alpha is 5%, the level of significance. So your confidence interval is 95% for the population parameter beta 1. Then you compute the relevant t statistic corresponding to this critical value of alpha by 2 on this side, and here alpha by 2 on this side. So you compute the critical t value. So let's call on this side, this is minus t alpha by 2, this will be negative. So for example, for 95%, here the relevant t statistic will be corresponding to a 2.5% value, and on the right side it will be corresponding to a 97.5% value. If your computed t statistic for the coefficient, if the computed t statistic, which is beta 1 estimate of beta 1 minus 0 upon its standard deviation of beta 1 hat, this number, this is the t statistic that you compute for the sample. If it is greater than or falls in this region, greater than this value or lower than this value and fall in this region, then you reject the null H0. You don't say that I accept the null, but you reject the null. You reject the null or fail to reject the null. You don't say that you accept the null. Either you say I fail to reject the null or you reject the null. So if you reject the null, then you say that this variable affects y. If you fail to reject the null, that means your parameters fall in this confidence region. Then you fail to reject the null and say x does not affect y. In this video, we'll discuss some of the other functional forms of OLS regression that are nonlinear in nature, and we'll also discuss how to transform them for suitable estimation with OLS regression procedure. To begin with, we'll have a look at some of the log linear or log-log formations. For example, have a look at this expression yi equal to beta 1 times xi to the power beta 2 into e to the power mu I. Now, in order to estimate this, notice the parameters are of nonlinear form, and therefore if we take the natural log transformation of this expression on both sides, left hand side and the right hand side, on the left hand side we have ln yi, on the right hand side we have ln of beta 1 plus beta 2 times ln of xi plus mu I, which can be further transformed into yi dash equal to alpha plus beta 2 times xi dash plus mu I. Now this final transformed model, notice it is linear in parameters alpha and beta 2, and therefore if we estimate this model through OLS regression procedure, the interpretation of beta 2 here is important, which is of coefficient of interest, which is beta 2 measures the percentage change in yi for a percentage change in xi. Because this is log-log transformation, that is why it is percentage change in yi for a given percentage change in xi. But for all times to come, remember that the original nature of equation has transformed. So if you wanted to estimate this beta 2, the interpretation with respect to original xi and this xi dash is different. Nonetheless, this expression can be estimated with the OLS regression procedure. Now have a look at this another expression for which we are going to use log-lin transformation, yt equal to y naught plus 1 plus r raised to the power t. If we take the natural log and transform the model as below, here natural log of yt equal to beta 1 plus t times beta 2, because it was 1 plus r to the power t, the logarithm transformation has made it in this form. Now please note, this is a semi-log model because the dependent variable yt is in log form while the independent variable t is not in log form, and therefore the interpretation of beta 2 is as follows. Beta 2 measures percentage or proportional change in yt for a given absolute change in t. However, if your coefficient of interest were y0 and 1 plus r, the interpretation is not exactly identical to them. Nonetheless, this model can be transformed with the help of OLS procedure. Also, this was a log-lin transformation, a vice versa interpretation for lin-log model, as we can see here, that is given change, absolute change in yt for a percentage change in xt will be applicable to a model of this kind, where xt, the dependent variable, is in the log form, while yt, the independent variable, is not in log form, and therefore the interpretation of beta 2 will be, like we said, absolute change in yt for a percentage or relative change in xt. To summarize this video, we noted that there are certain expressions which are not exactly linear in parameters. However, with some transformations such as taking log on both sides can transform them into different or resulting format which is linear in parameters, and therefore the resulting format or the transformed expression can be estimated using OLS regression procedure. However, the interpretation of coefficient from this transformed equation may not be identical to the original equation. Nonetheless, it is still useful for estimating the coefficients and making policy decisions and from such perspectives. Among supervised learning algorithms, regression algorithm is a very important tool employed in finance domain for applications such as forecasting security prices or credit scoring. Regression algorithms can be run with only two variables, one independent and one dependent, which is known as simple linear regression, or with more than two variables, which is called as multiple linear regression. The key variables in a regression model include a dependent variable, one or more independent variables, coefficients of these variables, and an error term. The error term accounts for the variation in the dependent variable that cannot be explained by the model. While regression analysis can provide the statistical significance of the relationship, the direction of causality should come a priori from the theoretical underpinnings. Refer to the rain versus crop example in this lesson. Ordinary least square or OLS is the most often employed method to estimate a regression model, which involves minimizing residual sum of squares. OLS estimation or ordinary least square estimation of regression involves 10 key assumptions. The most important assumptions here include linearity in parameters, exogeneity of independent variables, zero conditional mean of the error or residual term, homoscedasticity of error variances, absence of multicollinearity, no autocorrelation across error terms, no correlation between error and dependent variables. If these assumptions are held, then OLS estimators are referred to as BLUE, that is best linear, unbiased and efficient estimates. The statistical significance of OLS estimators is determined through hypothesis testing of coefficients individually. This requires normality assumption of the error, that is residuals. Very often, the model is not linear and may require some kind of transformation to make it linear, which can be subsequently estimated through OLS. However, the interpretation of coefficients also change with such transformations.